The first part of this video series covered the 0th and 1st laws of thermodynamics. Moving on, the second law describes how energy is transferred. It says, when two initially isolated systems in separate but nearby regions of space, each in thermodynamic equilibrium in itself but not necessarily with each other, are then allowed to interact, they will eventually reach a mutual thermodynamic equilibrium. The sum of the entropies of the initially isolated systems is less than or equal to the total entropy of the final combination. Equality occurs just when the two original systems have all their respective intensive variables equal, then the final system also has the same values. Let's break this down. The first part of the second law defines parameters. It gives two things that are different temperatures and are separated, but are allowed to come together. It goes on to say that the thing with more energy will give energy to the thing with less energy until the two are the same. Now let's talk about the idea of entropy, which is brought up. We're going to discard the typical idea of disorder to make it easier to understand. We'll think of entropy as dispersal of energy. Unless prevented from doing so, energy will disperse. A ball will drop to the ground unless held up in the air. Hot water and cold water will mix to make warm water unless kept separate. When energy disperses, entropy increases. The more energy is dispersed, the less is available to react. Gasoline has a lot of energy to react, especially when mixed with air. But when it combusts, energy is dispersed and the resulting carbon dioxide and water have more entropy than the gasoline and less energy to use for reaction. In general, gases have greater entropy than liquids, which have greater entropy than solids. This leads us to the third law of thermodynamics, which says the entropy of a perfect crystal at absolute zero is exactly equal to zero. This makes sense. If everything is at a minimum energy state and is perfectly arranged in a crystal structure, it has no other possible configurations, and thus no energy to disperse, making its entropy zero. Hopefully this video helped clear things up about thermodynamics. I'll see you next time.